Okay, this is chapter 4, file systems. We have been looking at operating systems in terms of abstracting the CPU first, and we abstracted the memory. Now we are gonna talk about abstracting the file systems files. That's the third major part of the major function of the operating system. Provide abstraction for the memory, provide abstraction for the CPUs, and provide abstraction for the files. That's what we are going to do. Okay. So the main motivation for the file system is this. Okay. When you power off your computer, all of your data in your memory goes away. You cannot keep them in the memory all the time because we have volatile memory in the computer as the main memory. So one thing is that in order to do something useful, it must be possible to survive the termination of a process. When I terminate my process, okay, when I terminate my process, the data that I produce should survive. So I need a permanent place to store my data. That's one of the requirement of the files. And the other one is that I need to store very large amount of information. I mean, the main memory nowadays is like 8 gigs, 8 gigs or 16 gigs or even 64 gigs. These are not large enough to hold very large data, like all the movies published this year. I mean, you need very large data. That's the second requirement for a long-term information storage. Store a very large amount of information. Then we need to share this stored information among many processes concurrently. That's the third requirement. So all of these three, okay, can be solved with a new abstraction. It's called file or file system. Okay. So that's what this chapter is going to look at. From the beginning of the semester, we talked about operating system. Operating systems are good for two things. One of them is that resource management, right? Managing all the resources of your hardware. The second one is that abstracting the hardware so that I can manage my processes and or my programs. I don't have to deal with the complexities of the hardware. So, operating system abstracted away the concept of processor to create abstraction of a process and threads. Okay. So that's one thing that we looked at. We abstracted the complexities of the processor. We might have one processor or two processors or many processors. It doesn't matter. We abstracted it and we came up with this idea of process and the threads. And second, what we did was memory is something very complex too. And we abstracted away the complexity of the physical memory, and we came up with the virtual address spaces. And now we are going to look at this new abstraction technique called the file. Okay. So together, abstraction of the processes and the address space and the files. These three are the most important concept relating to the operating system. Okay. So one is the processes. You know about your processes. Then you know about the address spaces and the files. These three are the main things, most important concepts relating to operating systems. If you really understand all of these three, then that means that you are in your way to becoming an operating system expert. This is completely from the book. Okay, this is completely from the book. If you know how to handle your processes, and if you know how the memory works, abstracted memory works, and if you know how the files are handled in an operating system, then you are becoming an operating system expert. The rest of them is kind of supporting structure for the rest of these three. Okay, so three things important for an operating system. So let's look at these files. Usually the files are read like memory. I mean, when you read the memory, you read it word by word, right? One word after the other word or the random access word. And in the file systems, we read the files by block by block. We say that read block K and write block K. Okay. So this is the main abstraction that we're going to use for the files, but the complexity of the file is different. So we are gonna look at how we are doing all these complex handlings. Okay. When we are doing these two simple stuff, read block K and write block K, many things, many questions will come to our mind. How do you find the information that we are looking at? That's one thing. Okay. How do we find the information that we are trying to find? And how do we keep one user from reading another user's data? It's like the memory protection, but this is now disk file protection. Okay. And how do you know which blocks are free and how do you allocate all of that stuff? So most of the problems that we had with the memories, they still exist for the files too, but the environment is different. In the memory we have the speed issues between the cache and the CPU and etc. For the files it's a little bit different. It's a very large storage space. And for the memory, the technology is almost the same for all kinds of memory. For the files, we could have many different storage medium like the disks or tape drives or the SSD storage or the CD-ROMs or the whatever comes to your mind. So the technology is very different. So the file systems have their own complications that we need to deal with. Okay. So abstracting the file systems is similar to abstracting the memory, but it has its own problems. Okay, design decisions, some stuff we are going to look at today. The names of the files, okay, so we know how to name the files, but the different operating systems behave differently. The structure of the, there should not be a U, okay, structure of the file system differs from operating system to operating system. Also, within a single operating system, we might have different structured files too. Access control, okay, and the versioning. I can have different file versions. There are some operating systems that can support directly the versioning. For example, there's operating system called Plan 9. It was a revolutionary operating system, but it didn't catch up. Nobody used it. So it doesn't erase anything, okay? It just keeps versions of all the files, like Dropbox. You know, in Dropbox, you have all the versions of your file for the last 2 months, right? So it never erases anything. It just keeps the versions of each file, version 1, version 2, version 3, or it versions the files by the date, okay? So this operating system does the same thing. Fault recovery, I mean, whatever you do, there will be crashes, okay? There will be inconsistencies. There will be some other problems with your file system. So since you are storing your files to be used for a long time, sooner or later you will have to do some fault recovery because you are going to have some computer crashes. And we have some file operations and many more design decisions we will discuss in this chapter. Okay, let's look at this file name stuff. The first thing with the file names with different operating systems is that case sensitivity. When you name a file, this for some systems, this file name is different from this file name. So this is called case sensitivity. For older operating systems like the MS-DOS, these two are the same, but for Unix, these are different files. Sometimes it is very confusing to have these type of files in the same directory. But Unix allows these kind of files to exist in the same directory. It's like the C variables. So case sensitivity is different for different file systems. Then we have the issue of extensions. Extension is whatever you have. If this is my file name, and I say .c, .c is the extension, and I can have many different extensions, and the extensions most of the time show the file type. For example, we know that This is a C file name, okay, a C program file. It contains C code, okay. And some operating system knows this from the kernel. In Unix, the extensions are uninterpreted. Unix doesn't know if this is a C file or not, okay. In Unix, this is not interpreted. So .c doesn't mean anything other than a file name. So how do we know that it's a C file? We know it. The compiler, C compiler knows it, but the operating system kernel doesn't know that it's a C file. It doesn't care it's a C file or something else. So for Linux or Unix, it is uninterpreted, and it is not required actually. I mean, you don't have to have an extension for Unix for a file name. Okay, so the file names are not required in Unix. For some systems, it is not permitted at all. You cannot have any extensions. Sometimes we have these length issues. For example, for the MS-DOS systems, we have only 8 characters, right? 8 characters, then 3 characters for the extension. This was the case for the Windows systems actually, before Windows 95 or something. So even today, some people try to rename their files with this restriction. They use only 8 characters because that's a kind of a people got used to this kind of convention, so they keep using it. So it changes from operating system to operating system. For Windows, the extensions are required and it is interpreted. That means that the kernel, Windows kernel knows that this is a C file, okay? Windows kernel knows that when you say a.exe, okay, it knows that it's an executable file, okay? It knows that it's an executable file by looking at the extension. Unix doesn't know that, okay? Unix doesn't know that this is an executable file or some other file. I mean, to make something executable in Unix, what you need to do, you need to set its execution bit. Remember, read, write, okay, and execute. There is an execute bit for each file. You need to set that execute bit to 1, so that the Unix shell can execute your file. So naming conventions are different. Depending on your operating system, the interpretation of the extensions are different, if it is permitted or not permitted. You need to know your the character set, okay, character set. I mean, underscore is okay for a file, dot is okay for a file. Some characters like I mean, if you try to make a file name like this, ABC1 is okay, but ABC1 less than sign dot C, this is not okay, because this is a very special character for Unix Linux environment. You cannot have this kind of a file name, okay? So depending on the operating system, the file names might be different. Some file systems that we use most of the time, FAT16, okay, it comes from the MS-DOS days. Then we have the 32-bit version of this file system. And we have the NTFS, very popular among the Windows environment. Then with the Windows 8, REFS, resilient file system. This is used by the server systems, so it is not very popular among the regular users of the Windows. So we have similar file systems for the Linux Unix environments. So each operating system might share some file system format from some other systems to be compatible, or they might invent its own file system. And we are going to look at these file systems one by one in this chapter. Okay, any questions so far? So as I said, what we are trying to do is abstract all these complications of the file handling, so that our programs can use the services provided by the operating system in a very easy and convenient way. Okay, there are a few extensions, some meanings assigned to these extensions. Locale file, C source program, GIF graphics format, HEF file, HTML file, JPEG, and we all know these, right? You know what this? You know what this is? PS. PostScript file. PS was the standard before the PDF for sharing documents. Okay. Even today we use PS for. Some printers can interpret these PS code, PostScript code. I mean, if you take a PS file and open it with an editor like the gedit, okay, you will see that it's a program actually. PostScript is a scripting language, okay. So it defines how to draw a page. You can write your own code in PostScript. I remember I have written code in PostScript. It's tag-based language. It's very difficult to write. So usually people don't write programs in PostScript, but how about this one? LaTeX, okay. Anybody knows how to write LaTeX documents? Okay, so try to use this once or twice at least in your lifetime, because this used to be very popular. Even today, most of the academicians, they use this kind of files to write their own scientific papers, and we know this, and we know that. There are many extensions for the Windows system. Remember, Windows has some kind of a operating system utility that assigns programs to handle these type of extensions, right? So it is part of the operating system. It's part of the operating system to know what the extensions of the files are. But for Unix doesn't care what the extensions are. The extensions are meaningless for the Unix kernel. But for Windows kernel, they are valuable. They know what that means. That doesn't mean that Unix, some part of the Unix doesn't know about the extension. The kernel doesn't know it, but the graphics shell, like the KDE and other kind of graphic shells, GUIs, they know how to handle these kind of files, but the kernel doesn't know. Okay, file structures. How the files are structured are different, and they are different from system to system. Herkes beni imzaladı mı? Sen imzaladın mı? İmzalamadın mı? Dersten sonra geri imza, tamam. So the file structures are different from operating system to operating system. How the files are structured on the medium that on which they are stored. It depends on the operating system. It depends on the operating system's version actually. On all systems, files were a sequence of records, initially image of punch cards or printed lines. So the files are like, I mean, remember those, we talked about those punch cards. This is the structure of the punch card. You have all these letters A, B, C, D. It goes like that, and 1, 2, 3, 4, 5, and 9 here. So there are marks. Okay. If you punch this part and if you punch this part and it goes like that. I mean, if you, I think I did it. No. It wasn't like that, no. How do you write programs like that? This is A, and then for the first, yeah, okay. So that means that going this way, let's say for this one, so for this line I have B and A and B. It goes like that. So this card can hold me. Let's say at the end I have 9 here. This card can hold 8 characters. Okay. So when you read this card from the card reader, you have 80 characters, and you store these 80 characters in your file. So initially for the old systems, the files were word sequence of records, and each record is 80 characters long. Okay, images of punch cards or printer lines. Or if you are sending something to the printer can print 132 characters per line. So your files were structured by the records of this size, and if you are using for import, files are structured by the records of this size. Okay. So when we stopped using these punch cards, we started using directly from the keyboards and from the other files. The Unix said that randomly accessible sequences of bytes. So we lost all the sequence of records, and Linux and other modern operating system started using sequences of bytes to give a structure to a file. Okay, some systems are page oriented, like the paging of the memory. They are paging the files. Okay, so remember for the paging, we modeled our memory as a sequence of pages. Not all the pages have to be in the memory, and the similar stuff it is tried for the operating system for the file handling. Okay, the book describes 3 types of file structures. Okay, the first one is this one, A. This is the one that we are using. Okay, when we read a file, we say that, okay, read the first byte, then the second byte, then the third byte, right? If you are using it character by character, I can read this character by character, or you could say that read me 100 bytes, right? You can say that. Remember the C read function. I can read any number of bytes from this file. Or there are some other operating system that keeps its files structured by the records, like those punch card records. Or sometimes for the management of the database systems, sometimes files are organized